So let's do a problem involving both forces and one-dimensional motion. So we'll do a problem that does actually a free body analysis that you have to do and one-dimensional acceleration. It's kind of the culmination of the last 5 chapters, everything we've been doing in the course up till now. So my son really likes Lightning McQueen and Mater, and so I thought I'd like to do a problem on that because that would make him really happy. So let's consider Lightning McQueen. Say he has a mass of something like 1,500 kilograms, and he's being towed by Mater by a cable that is held at 21-degree angle. There's a friction force of 320 newtons that opposes Lightning McQueen's motion. So what Mater would kind of like to know in adjusting his motor is what is the tension in the cable if McQueen accelerates from rest to 12 meters per second in around 9 seconds. So that's our setup. We have a car, Lightning McQueen, being towed at an angle, and we want to know what the tension in the cable is. So let's approach this problem like we approach any other problem. Namely, let's approach it and draw a picture. So the first thing we should do is draw a force identification diagram picture. So let's draw a... sorry, I need to get my pen. So let's draw the car. Lightning McQueen, that's my interpretation of Lightning McQueen, being pulled at an angle by a cable, and that's being pulled at some angle, call it theta for now. So let's identify the forces acting on Lightning McQueen. So there's a contact force, there's tension in the cable, so we'll call that T. There's contact forces where Lightning McQueen touches the ground, which is the normal force, which we'll call N. And then there's friction force. And we haven't been told even what kind of friction it is. Let's just call it little f vector, just to give it a name. There's also, as usual, a long-range force, namely weight, that's floating around. So now we have our force identification diagram. Let's draw our free body diagram as well. Oh, sorry, before we even do that, let's identify the direction of the acceleration. So if Lightning McQueen's being pulled that way, we expect an acceleration that way. So now we can draw our free body diagram. So I'm going to try and squeeze it in right over here. So we draw our coordinate axes, our y and x directions. And Lightning McQueen now is just a dot at the center. So we have a normal force up, and weight is down. There's some tension pulling at an angle theta from the horizontal. And there's some friction force opposing the motion. Okay. So that's what we know about the forces acting on Lightning McQueen. But Lightning McQueen, as we're told, is also accelerating, and we're told something about how Lightning McQueen is moving. Namely, McQueen goes from rest to 12 meters per second in 9 seconds. So in addition to drawing force identification diagram and free body diagram, we're going to need to draw a motion diagram as well. So let's draw a motion diagram. So here's the road, and Lightning McQueen, say, starts here at some initial position, let's call that 0 meters, and an initial time 0 seconds. And we're told that Lightning McQueen starts from rest, and so his initial velocity is 0 meters per second. We're told that Lightning McQueen ends at some final position, so we don't know what that final position is. We do know that whatever it is, it takes 9 seconds to get there, and that the final velocity in the x direction is ultimately 12 meters per second. And that also implies, just by thinking about how this could happen, that Lightning McQueen has to be accelerating to the right just as we had drawn in the direction of the acceleration above on our force identification diagram. So the accelerations are all to the right, which also means that the net force, I'll put it here on our free body diagram, is also ultimately to the right. Okay, so now we've labeled everything. Let's list the things we know and the things we don't know, and see what we need to find. So we know the mass of Lightning McQueen. We're told it's 1,500 kilograms. We know the angle that he's being pulled at, just 21 degrees. We know the magnitude of the friction force, which we're told was 320 newtons. We also know things about the kinematics, not just the forces. About the kinematics, we know the initial position, the initial time, the initial velocity. We know the final time and the final velocity. And, okay, so then what else is there? Well, we don't know what the tension is, T. In fact, that's what we're trying to find. But as an intermediate step, I think what we're also going to need to find is the magnitude of the acceleration in the x direction, ax. Okay, so we're all set up. Let's set this up as if it was a force problem and try and solve it and see what we need to know in order to solve this as a force problem. So let's go down to solving. Whenever we solve a force problem, we write down the forces in the x and the y direction. So in the x direction, looking at our free body diagram, we have tension in the x direction, some component of tension which we'll have to find in the x direction. And we have frictional force in the x direction, pointing in actually the negative x direction. And by Newton's second law, that's equal to mass times the acceleration in the x direction. In the y direction, we have a normal force, pointing in the positive y direction. We have weight, there's our free body diagram, we have weight pointing in the negative y direction. And we also have a component of the tension pointing in the positive y direction. So we have a tension in the y direction. And that's all equal to mass times acceleration in the y direction. Now, since Lightning McQueen is only accelerating to the right, Lightning isn't accelerating up or down, he's staying on the road, then the y acceleration should be 0. So not accelerating in the y direction. Again, it didn't immediately say this or directly say this in the problem. We have to infer it based on what's going on physically. We have to think about the problem and realize there can't be any acceleration in the y direction. Okay, so we need to, we've written forces in terms of the x and y components of tension, and so we're going to need to look at that more carefully. So we need to redraw our triangle, our tension triangle. So our tension triangle is the magnitude of the tension along the hypotenuse, angle theta, and then the x component and the y component. And that's a right angle there. So using our trig, we find that cosine of the angle theta is the tension in the x direction over the magnitude. So the x component of tension is the magnitude of tension times cosine of the angle. Then we can do the same thing for sine of the angle theta to find the y component. So the y component of tension is t times sine of the angle theta. Okay, so we have the x component and the y component of the tensions, and we can plug them now down into our expressions for the forces. But I can actually see already that the y direction actually isn't going to give us much. It's not going to tell us a whole lot. So let's write that explicitly. The y direction for this particular problem is going to be irrelevant. We're going to be able to solve everything just by looking at the x direction. And that usually happens when something's just moving along in one direction, like it's moving along a road. Oftentimes, the y direction, unless we're asked specifically what is the normal force, then we may not need to use that y direction. So let's rewrite the forces in the x direction. So the forces in the x direction, it's the x component of tension, so T times cosine of the angle theta, minus the friction force, which we know, is equal to mass times the acceleration in the x direction. So let's go back to what we were actually trying to do in this problem from the beginning. So from the beginning, what we're really after, what we're really told, is find the tension. So we really want to find the tension T. So in the expression that we just wrote down for forces, we could solve this for T if we knew the x acceleration. So let's go ahead and do that, assuming that we knew what the x acceleration was. Then T is, well, it's the mass times the x acceleration plus the friction force, all divided by this cosine theta angle. But as I just said, this is assuming we knew the acceleration in the x direction. So we need to find that. We need to do something to find the acceleration in the x direction. So that's going to be our central problem now. What is the acceleration in the x direction? And for that, we're going to use 1D acceleration problem-solving methods. So this problem was not only a force problem, but it was a one-dimensional acceleration problem. So let's go back to the diagram we drew above, the motion diagram we drew above, where McQueen starts at rest, accelerates to the right, and ends at some final speed after 9 seconds. So we want to find acceleration, and we're given the initial and final velocities and the initial and final time. So we look at our equation sheet and say, okay, how would we find from those three main equations the acceleration if we knew the velocities and the time? And we see that we can use the expression that the final x velocity is equal to the initial x velocity plus the acceleration times the change in time. Or rewritten for the numbers we have here, we find that this is 12 meters per second. It's equal to the initial velocity, 0 meters per second, plus the unknown acceleration times the 9 seconds. We can solve this for the x acceleration. We find the x acceleration is 12 meters per second divided by 9 seconds, or the two significant figures, 1.3 meters per second squared. Now that we have the x acceleration, we can plug that in for the expression for the tension that we had above. So we can put it in our expression, the tension is equal to mass times whatever this acceleration was, plus friction force over cosine of the angle theta. So just plugging those in, we get 1,500 kilograms times 1.3 meters per second squared, plus the friction force, which was 320 newtons, all divided by cosine of the angle 21 degrees. That looks like 210. Let me make it 21 degrees. There we go. And I put all these in, and at the end of the day, to two significant figures, we get that the tension in the cable is around 2,400 newtons. And that seems reasonable. It's a fairly large amount to pull a fairly large car and to make it accelerate around 1 meter per second squared.